Now I teach least squares prediction, which is a method for predicting or interpolating the gravity data. To do so, consider a grid of data, gravity anomaly, for example, and I have gravity anomaly in each cell, and the point is to estimate gravity anomaly at the cell, central cell. Therefore, I define a estimator or gravity anomaly estimator delta G cap as a summation with a weight I, AI, delta Gi. This is the estimator that I will use to estimate the gravity anomaly in the central cell. In other words, it means that I use the data around to predict the data at the center. But how this AI can be estimated? It should be estimated in such a way that the bias and the error of this estimator is minimized. So how can we do that? Let us drive the error equation for this estimator. So summation over I, or the cells, the coefficient AI delta GI, plus the error of the delta GI. Epsilon is the error of the gravity data. And this term minus delta G at the prediction point. I have to write this because it's otherwise I cannot make an error equation. This estimator with this random part, which is the epsilon is a random part, but this estimator should be as close as possible to the true value of the gravity anomaly. Of course, we don't have it, but we have to write the error equation in that way. If I expand this error equation, I will come to this summation over I, AI, epsilon I, plus summation over I, AI, delta GI, minus the true value of the predicted gravity anomaly. The last two terms are actually the bias of the estimator, and the first term is the error. But if I take the average, it will be zero for the error term. I don't want to have the error zero. Then I have to square it based. Then if I square this one, it will be summation over I, AI, epsilon I, summation over J, AJ, epsilon J, the square root of the first term, plus the square of the second term, or a square of the first term multiplied to the second term. Then it will be square of the second term to the first term, but I can write them once. Instead, I say 2 times of the 2 times of this multiplication and square of the bias term. Summation over J, AJ, delta GJ, minus delta GP. Now I should take the average over the errors, or summation over of the error equation. So it is least squares. It's the summation of all the square terms. If I take the average, I will come to, let me explain this before. Statistical expectation of a stochastic random variable will be zero. Not this is Gaussian. It's errors of Gaussian. And if we take the statistical expectation of epsilon I with I, it will be the variance. And statistical expectation of EI, epsilon I and epsilon J will be zero. It means that the errors are not correlated. Based on this property, the second term of the error equation will be zero. And the first term will be simplified to summation over AI squared and the variance. Now I simplify the last term of the error equation. Summation over first over I, summation over J, AI, AJ, and the averaging operator of delta GI and delta GJ. Now I continue minus minus delta GIJ AI M delta GI delta GP 2 times plus average of delta GP delta GP. Now this error list squares should be these squared errors should be minimized. Now these squared errors should be minimized. The derivative with respect to AK, which is will be not AI2, okay, I variance. Now this term should be 0 to obtain AI. This term, M delta GI delta GP, is a covariance between delta GI and delta GP, and the other term here is actually the covariance between delta GI and delta GJ. If I solve this equation for AI, I will get cap I is the covariance delta G I delta G P divided by covariance delta G I and delta G J plus the variance. This first term, the covariance with delta Gi and delta Gp is actually called cross covariance, and delta Gi and delta Gj or delta Gi is called autocovariance. P is the prediction space, and the cross covariance actually is defined between the prediction space P and Q is the measurement space. But autocovariance is defined for Q space or the measurement space. In that case, I write the estimator, and now I insert a what I have estimated for AI. Here is the covariance delta GI, delta GP, and covariance delta GI, delta GA plus the summation plus the variance times delta GI. That's actually the estimator, the least square estimator for predicting gravity anomaly. The 2 was missing here. Now I explain it. How can we use this one in practice? What we should understand for least square prediction is the prediction space and measurement space. Let me call this measurement space, and the other one is the prediction space here. And what I need here is a cross covariance function between these two spaces. Yes, cross covariance CPQ. CP is covariance. And also autocovariance function in the measurement space. I need these two cross covariance actually express how these two spaces are connected to each other. And autocovariance means express how the measurements are correlated to each other. If I write it in matrix form, I can say that the predicted vector of gravity anomaly will be the cross covariance between the predicted and measurement space plus the autocovariance of the measurement space plus the error covariance matrix of the measurements inverse times the vector of measurements. This is the principle of least squares prediction.